the 12th lecture from chapter number 9. We are studying VLSI design. In our last lecture, we studied domino chains or domino logic, and we studied that to cascade different gates that are dynamic in nature. We cannot cascade them together because different gates can have different time constants tau, and the preceding gate may have a larger time constant than the following gate, and they may cause an erroneous or wrong output. So that is a small recap of our last lecture. To combat that problem, we introduced domino logic, where we introduce a static NOT gate between stages. Here is a stage of dynamic CMOS implementation. Here is another stage, and we keep on introducing static inverters in between. And in our last lecture, we studied how these static inverters work to help in cascading dynamic CMOS gates together, and we get the correct output. Right. But we must also understand that different gates in a domino chain may have different tau, and we have to wait till the largest value of tau, unless the last gate is unless the last gate has completed discharge. If it has to discharge, this means that we have a pre-charge interval smaller compared to the evaluate interval, because during this evaluate interval we have to wait for the slowest gate to discharge. So we have a longer evaluate interval compared to the pre-charge. And we have also studied in lecture 9, 10, 2 lectures before, that if we have a large value of evaluate interval, we come across charge leakage and charge sharing problems that we studied in lecture 9, 10. So having larger evaluate interval has both its advantages and disadvantages. The advantage is that we are giving enough time for the slowest gate to discharge. This is the advantage of having a longer evaluate interval, and the disadvantage is that the dynamic gates here and here, they lose their output voltage due to charge sharing and charge leakage. So how can we address this problem? How can we keep them from charge sharing and charge leakage if we have to have a longer evaluate interval? Let's see, how do we do that? Evaluate interval must be large enough so that every stage can discharge. This is part of our recap. That will worsen the charge sharing problem. We studied 2 lectures before like this. We studied here that we have a ground here, and this charge sharing problem worsens because if A and B are 1, these capacitances, this becomes one node. That if we ignore the resistances of each transistor, and then we have a discharging current flowing through, which settles V out to a value Vf that is lesser than VDD. This was studied in detail in lecture 9, 10. Right. So the solution then, what's the solution? What's the solution? You have to have a longer evaluate interval, but how can we keep the output of dynamic gates from being discharged? So what is the solution then? So we want to have a larger evaluate interval, and we want the output of the dynamic gates to be at the voltage they have. They must have. They have. They are. If they are at VDD, if the output is at VDD, it remains at VDD. It should not be discharged. The capacitance should not be discharged, and the voltage should not drop to a value lesser than VDD. So how can we avoid? In other words, how can we avoid charge sharing problem? So charge keepers give us a way to address charge sharing problem, the decrease of voltage due to charge sharing. Charge keepers, they provide a pull-up path because the voltage at the output is decreasing from VDD, so we need to pull it up to VDD again through some combination of transistors or gates, etc. The output of a dynamic gate is kept at VDD by introducing an extra pull-up path that is done using charge keepers. Let's see, there are two types of charge keepers: single PMOS based charge keepers, and we have feedback based charge keepers. Let's see both of these types of charge keepers one by one. A single PMOS based charge keeper is the one. Let me take it into the screen, the full circuit. Right, now it is there. Right, so this is the a general block diagram of a dynamic CMOS circuit, and this is the inverter that completes this domino chain, and it goes on. It's a part of a chain. So we introduce at the output a PMOS transistor MP prime. This MP prime is a PMOS transistor that is always on, like we have in case of pseudo NMOS. It's always on. Why it is always on? Because once this PMOS is on, the VDD that is there at the source is here. VDD is available here. So at the drain of this MP prime, we have a VDD unless the source is connected to VDD and the gate is connected to ground. It's on, and VDD is available at the output. So it keeps the output at VDD, and it doesn't allow this output voltage VDD to be lower than its value, lower than output voltage. It doesn't allow this V out to go below VDD. Even if we introduce some capacitances here due to the reason certain inputs are on, even then the output doesn't go below VDD, because there is a path that continuously introducing this VDD here. So this is one way we can keep the output at VDD and can have a longer evaluate interval. But it has a disadvantage, and that is obvious. That's the same disadvantage that we had in case of pseudo NMOS, where we had a PMOS that is always on. So the obvious disadvantage is a smaller VOL, a VOL, sorry, a larger VOL, a VOL that is greater than 0 volts. That is greater than 0 volts. So feedback based charge keepers is the other class of charge keepers that we can use. to keep the output at VDD, to keep the output at VDD, even if we have a longer evaluate interval. So this V out during pre-charge is at VDD, and if during this evaluate period, the longer evaluate period, it finds a discharge, a path of discharge through this NMOS array, and the voltage tries to be below VDD. This VDD is fed here, and it converts to 0 volts here at the ground. And when this 0 volt is applied at the gate of this MP prime, MP prime, we get a VDD here. So even if the voltage is a bit smaller due to discharge, a bit smaller than VDD, maybe if VDD is 5 volt, and if it drops down to maybe 4.8 volts, even then if we apply this voltage here, we get a 0 volts here, and then it is replaced with VDD once again. So this feedback path, through this feedback path, we are continuously getting this VDD here. So it seems to be a better circuit, because if V out is low during evaluation interval, VOL becomes 0 volts. If this NMOS in this evaluation period, in this evaluation interval, if the input is such that the output has to be at 0 volts, then this VDD, if somehow discharges through this NMOS path, this NMOS array, and if it is below a certain value, maybe below VM, middle voltage, the output maybe the output is 0, and 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 we get a VOL that is 0 volts. So these are two types of charge keepers that we use to maintain the voltage at the output of a dynamic gate at VDD. We'll continue studying high-speed logic circuits in our upcoming lectures. Thank you.